Hello everyone, my name is Jing Xuan. Today I will present our paper, Learning Fast and Precise Numerical Analysis. This is a joint work with Gagandeep, Marcus, and Martin at the Department of Computer Science, ETH Zurich. Numerical domains consist of abstract elements and abstract transformers, and is a key part in numerical programming analysis. Given an input program, numerical programming analysis works by passing abstract elements through a sequence of abstract transformers. The analysis outputs numerical program invariants, which can be used to prove various kinds of safety properties of programs. Developing a practically useful numerical domain is challenging, as one needs to carefully balance the cost and expressivity of the domain. Interval domain has low costs but only captures non-relational invariants. Polyhedra is the most expressive linear relational domain, but comes with worst-case exponential time and space complexity. Octagon is between the interval and the polyhedra domain. There are a number of techniques for speeding up existing domains without affecting the precision of the inferred invariants. Among those, online decomposition provides a generic solution for multiple domains. However, we found that analysis based on online decomposition has redundant computation, which unnecessarily slows down the analysis. Orthogonally, another line of research selectively loses some analysis precision for gaining performance. However, each of these works focuses on only one domain, and the precision loss can be large. Therefore, we want a generic method that lowers analysis costs significantly with minimal precision loss. The key idea of our work is to remove redundant computation from the analysis sequences. We now explain our observation on redundancy in numerical program analysis. Suppose we are about to analyze a program. Starting from the initial abstract element, we can apply the precise transformer or one approximate transformer. After applying a sequence of transformers, we obtain the numerical invariants. Different sequences may result in different precision of the invariants. In the bottom, green circles represent precise invariants, and red circles represent imprecise invariants. We obtain the precise invariants by always applying a precise transformer. However, since the precise transformer is expensive, the precise analysis is slow. To make the analysis fast, one can apply faster approximate transformers sometimes. However, this usually results in imprecise invariants, like the highlighted sequence. We also observe that it's likely to obtain the precise invariants by carefully applying approximate transformers. For example, in the two highlighted sequences. For these two sequences, even though the intermediate abstract elements are less precise than the precise sequence, the final invariants are the same as the precise sequence. Therefore, there is a redundancy in the precise sequence, as other sequences can achieve the same precision with less effort. Such redundancy can become the bottleneck of large programs. As we show later, our work brings more than 100x analysis speedup without affecting the precision of the inferred invariants for large Linux device drivers. With this observation, the challenge then is to define and selectively apply the approximate transformer to remove redundancy in the sequence of abstract transformers, which results in fast and precise analysis. We introduce Lait in this work. Lait is a learning-based transformer that removes redundant constraints from the expensive join transformer. We show how Lait works with an example. The join transformer here computes an over-approximation of the union of the two abstract elements. Lait represents the join output with an undirected graph. Each node in the graph represents the extracted features for each constraint. Features include measures for precision and the complexity of the abstract element and the constraint. Each edge captures the dependency between constraints. For example, The value 2 here means that the connected constraints share two variables. The graph captures the overall state of the abstract element. We input the graph into graph convolutional networks. The networks jointly consider all features and edges in the graph, and output for each constraint a Balaran decision, whether to keep or remove it. For example, we use green color to represent the constraints that the network decided to keep, and red color for the one to drop. Then we'll obtain the output of light, which has less constraints than the precise drawing output. Since the complexity of abstract transformers depends on the number of constraints in the input, the constraint removal by light can accelerate the analysis downstream. The key part of light is the graph convolutional networks deciding which constraints to drop, which essentially is a binary classifier for constraints in the abstract elements. To train the networks, we need a supervised dataset of graphs where the removed constraints are labeled true or false. True means that the removing the constraint does not affect the analysis precision, and false means that removing the constraints loses precision. On the right, we show one example graph in the dataset. The top right constraint is labeled true, meaning that it can be dropped, and other constraints are unlabeled. With such a dataset, we can train the networks with existing optimization techniques. Now we explain the steps to generate the dataset. Step 1 is to run precise analysis on training programs to obtain ground truth for precision. So here we have 3 programs, and the precise analysis generates 3 sequences and 3 sets of precise invariants. In step 2, we run approximate analysis with constraint removal on training programs. In the example, we approximate twice, marked with red arrows. Then we compare the precision of the inferred invariance between the precise analysis and the approximate analysis. For example, the solid approximation does not affect the precision of the invariance, but the dashed one makes the result invariance imprecise. The approximation in training is epsilon greedy, which means that we correlate with 1 minus epsilon probability, or we call a random removal policy with epsilon probability. In step 3, we label the removed constraints as true or false based on whether they affect the precision. In our example, the removed constraint in the solid approximation does not affect precision, and is so marked as true. The 2 removed constraints in the dashed approximation are labeled as false. With the labeled dataset, we can train the networks with existing optimization techniques. The learning algorithm is iterative, as step 2 and 3 can be run for multiple iterations. At each iteration, step 2 provides step 3 with more labeled data for training the networks. In turn, step 3 returns to step 2 a better trained network for running the approximate analysis. The trained network is gradually improved after each iteration. Now we present our evaluation on Lait. Lait is instantiated on the online decomposed Polyhedra and Octagon domains. The implementation is available in the current version of Elena. In the evaluation, we run analysis with the graph LLVM analyzer on SVConf benchmarks. We compile Lait with 3 baselines. The first is the version of Elena when we wrote the paper, which provides precise transformers and is used for obtaining the ground truth for precision. In other words, Lait tries to remove redundancy from the precise analysis with Elena. The second is PolyRL, an approximate Polyhedra analysis with reinforcement learning. The third is HC, a strand hand-created heuristic based on online decomposition for redundancy removal. Precision of the inferred invariance is measured by the percentage of program points where the inferred invariants are the same as Elena. We first present the results for Polyhedra analysis. We train Lait on 30 programs and show the testing results on 10 programs here. For each benchmark, we show the number of program points, time spent on analysis with ELINA. Then for HC, poly-RL and Lait, we show the speed up over ELINA and the precision of the inferred invariance. We highlight 4 programs in blue that are expensive to analyze with ELINA. For these 4 programs, Lait achieves up to 2 orders of magnitude speed up and 100% precision. That is to say, even though faster, Lait does not lose precision and infer the same invariance as ELINA at all program points for these 4 programs. This demonstrates ELINA's redundancy for analyzing these 4 programs, and Lait is able to correctly identify and remove redundant constraints. On the contrary, HC can achieve good speed up, but they sacrifice precision. Poly-RL can keep the precision, but the speed up is modest compared to Lait. For programs that are less expensive for ELINA to analyze, which usually indicates that they have less redundancy, Lait can keep the precision to close to original level. In general, Lait can balance well the trade-off between precision and speed for numerical analysis. The time complexity of Polyhedra analysis is exponential in the number of constraints in the input abstract elements. We gather statistics on the number of constraints in the sequence of abstract elements for each program and report its maximum and average value. In the table, we can see that Lait can effectively lower the maximum number of constraints in the analysis sequence, which means that Lait can solve the performance bottleneck. For example, for the first benchmark, the maximum value for ELINA is 267, and Lait reduces it to 33, giving an overall speed up of 53x, as we showed before. Poly-RL does not reduce the number much, only giving a speed up of 4x. H3 reduces the number even more than Lait. However, this leads to precision loss. We also run Lait on 207 programs for which ELINA timed out up to 2 hours to see whether Lait can push the limit of Polyhedra analysis. Over these 207 programs, HC finished 103, Poly-RL finished 50, Lait finished 125, more and faster than HC and Poly-RL. We also evaluate Lait on Octagon analysis. We train on 10 programs and present the results for the 10 testing programs. Even though ELINA's Octagon domain is already very fast on most benchmarks, Lait is still able to achieve an average of 1.3x speedup with close to original precision. On the contrary, HC does not maintain precision well. For the MD mode benchmark, where ELINA spent more than 1300 seconds, Lait achieves 28x speedup as its approximation makes the analysis converges faster. In the end, I would like to summarize the presentation. In this work, we observe redundancy in numerical program analysis. To exploit the observed redundancy for speeding up numerical analysis, we built Lait, a learning-based approximate joint transformer for removing redundant constraints. We introduced how to learn Lait with an iterative learning algorithm and showed the promising result of Lait and both Polyhedra and Octagon domain. Thanks for listening.